Hello everybody. Today we'll finally see all these stellar structure equations that we are deriving, the fruit out of it. Before I go into what we get out of solving the stellar structure equations, let us talk a little bit about what we started with in the stellar astrophysics, mainly the observations. We saw a few diagrams. One, if I remind you, is of mass versus luminosity. It looked something like that. These are log-log plots. The slope of the log-log plot was 2.5 here, 4.5 here, and 3 here. So these are observed curves, right? So L by L sun was given by M by M sun, say to the power nu. So mass luminosity diagrams. We also looked at the HR diagrams. So in this case, both of them increases in the normal ways. This I am drawing for open cluster here, which are the newer clusters. Here the temperature increases this way, and the y-axis is again luminosity. And remember, it was the main sequence was here, and then you have a little bit rising there and little bit falling there. The main sequence slope comes out to be around 5. Again, basically, if I say L by L sun, say if I call it alpha, that alpha is 5. And then when he said we looked at an older cluster, I'm plotting the same HR diagram here. Now for a globular cluster. Here we saw that the main sequence is depleted. This part is absent, and then there is something going that way. There is a little bit of region for the giants. So it is kind of obvious looking at these two that the stars which were there has gone in there. And these are high luminosity stars. High luminosity also means high mass. So we concluded that we had several conclusions from here. One is that high mass stars live lesser time. Because the low mass stars are still there. Low luminosity corresponds to low mass stars are still there. There's one more thing which is probably I forgot to mention, is that you get a minimum mass for the stars, like minimum luminosity for the stars. And again, this is a ballpark number. Star with luminosity less than 10 to the minus 3 L sun is never seen. Okay, so it is not a This is very important to point out. It is not a limitation of our observational capabilities. It is beyond the observational capabilities. It is that we have not seen such stars. Okay, so now these were the observations, and some of these observations we will like to explain in our today's discussion using the stellar structure equations. So let me write down the stellar structure equations now. So these are obviously we have discussed about the fact that we can consider thermal and thermodynamic equilibrium, thermal and dynamical equilibrium, and it is written in that spirit. dl by dm is q, and remember we said that q depends on rho and temperature in the following way. So let's call it n, because m is already used for mass. So q depends on rho and temperature, and n will depend on which nuclear reaction you are talking about. We assume ideal gas, so this is the equation of state. Let me give you an idea about n to start with. As I said, that n will depend on different nuclear reactions. Now, one such reaction is called pp chain. So I request you to look at what are these different chains. So for pp chains, so this is a set of nuclear reaction which happens in many of the stars. So n is equals to 4. So it will depend on T to the power 4. Then there are CNO cycles. Again, I request you to look at what are these, and you can also ask the question in sun which one is happening. So please look at the books for these things. Okay, so N is 4 in PP chain. CNO cycle, which happens at very larger temperature than where PP chain happens, N is 16. So for example, for PP chain to start, so T critical PP is about 4 into 10 to the 6 Kelvin. For CNO cycle to start, it has to wait for much larger temperature. All these numbers I request you to look at, because just I am going to give you only this much in this lecture. All right. What were our assumptions, or what are our assumptions? So one is the dynamical and thermal equilibrium. That is why we have written down these equations. The time derivatives has gone away. Second, all stars that makes of our main sequence. So remember that we are only talking about main sequence here. This is important. So if I go back to the HR diagram, we are only talking about the main sequence. We are not talking about the red giant branch or the dwarf branch or this bridge that goes from the main sequence to the red giant branch, etc. So in the main sequence, all stars we say that have same composition. Chi is independent of both R and T. Okay. It's independent of T that we said that in main sequence that we have discussed last time, because the nuclear time scale is very large. We are also assuming it's independent of R. It makes our life simple. If you don't consider it independent of R, there will be some variation which will change the numbers a little bit, not a lot. And we have used ideal gas equation of state. And additionally, kappa is also called opacity when you are dealing with three-dimensional radiative transfer. It's opacity per unit mass. So this is independent of radius. This actually gives some considerable change if you make it dependent on radius, but then you have to solve the equations, which will not do. As I said, that will not solve these equations, but still we'll get to what the solution is. Now, what are the variables we have? We have R, and everything is a function of M, which is my parameter. And luminosity. M varies. At the center of the star it is 0, at the surface it is 1. The only parameter, remember, we have is the mass of the star. Okay, everything else we will like to express in terms of the mass of the star. Now, how do I do it? So there's so complex equations. And you see, even it's not only complex, these are equations in terms of M or R. Their boundary conditions are also different. The pressure is maximum at the center where M equals to 0, and 0 at the boundary where M is maximum. Temperature is also similar, but luminosity is opposite, radius is opposite. So how do I deal with this? So the answer that people like Chandrasekhar and Eddington came is that we will do dimensional analysis. It's a very powerful tool. It tells you what is the dependence of something on something else. But in this case, it is even more powerful because all these parameters we actually know for one star, which is the sun, which is very near to us, our father, and we have measured all these parameters for the sun. So because we know all the parameters of the sun, what I can do is I can find out the dependencies. Let's maybe a little diversion. Say y equals some k times x1 to the power alpha y e to the y by beta or something like that. So say this is the dependencies. But this and this here I can figure out what is the dependence, but what I do not know here, that what is the value of k alpha and beta. But these we can find out because we will measure all these things for the sun, and then for the sun, from the values of the sun we can figure out what is k alpha and beta. So we are doing dimensional analysis in a particular case where we can actually calibrate our dimensional analysis. So we'll see how it goes along. So let us start. So what we do is the following. We define dimensionless quantities. So we define first a dimensionless mass, which is x. It's nothing but small m, which is the mass in the radius r, divided by the mass of the star. Once I do that, what I can do is the following. I can say, okay, the radius of the star, which is a function of m, I can write it instead of m, I can write it in terms of x. And the radius of the star is the one which I will use to make this radius dimensionless. So I define a dimensionless radius fr, which will depend on x, such that I can write r equals fr times r star. So fr is a dimensionless quantity. That is important. R star is the radius of the star. R is any radius in the star. Just the similar way, I can define P equals Fpx, and all of these quantities depend on m, which means it all depends on x, because x, the only dependence of x on the radius comes from the dependence of m on the radius. So this, I write P star. This P star can be any pressure. In this case, obviously, it will be the core pressure. Similarly, for the temperature, and this you can take either surface or the core temperature. It doesn't depend on what you take here. So this T star can be surface temperature or core temperature. All the entire analysis will work out for both of them. The only thing that will change is the value of Ft, which is said will fix using the solar values. Okay. Now what do I do with this? What I do is the simple one. I use one equation after other. So the first equation is dpdm equals gm by 4 pi r to the power 4. So let us do it for one and then write down things for the others. So dpdm is minus gm by 4 pi r to the 4. P I can replace by what I have in the right hand side. So it is Fp P star. P star obviously doesn't depend on the radius or the mass. And m is x times capital M. So what I can write now is P star equals I have two m's and r to the 4. What do I have in between these two? So let us make a little bit of gap here. So this is P star equals, I have G minus Gx by 4 pi Fr to the power 4 1 by dfp dx. Interestingly, G is a constant. Everything else is dimensionless in this square bracket. It's obvious that the number will depend on how f changes, fp changes with x, but it will still be a number. So I can say that P star varies as m2 r star to the power minus 4. Okay, so that is the first thing that we learned from the equation, first equation. But you see, I could have just written it down without doing all these things. Just looking at the first equation, I have dp by dm. So what I do is, instead of that, I write p star by m, which I take in the right hand side. I have 2m here, so this is m2, and then r to the power 4 in the denominator, so r minus 4. So I can directly write it this way for this equation. So let's do that for all the equations that I have. So the next one is dt dm. So I have t star, and m I can take in the right hand side. I have 1 by t cube in the right hand side, so this becomes to the power 4. So I have 1m, 1l star, and r to the minus 4. Please do this yourself and verify if you are getting exactly what I am writing down here. And then the L equation will give you m2 r minus 3 and t to the power n, depending on which nuclear reaction you are doing. And I have the equation of state, which will give me m r to the minus 3 t. If I have forgotten a star, so this is star. All of them are star. Okay, now I have, let's see how many variables I have. I should have the same number of variables as that the equation, such that I should be able to write down all of them in terms of m. So the variables I have are p, t, l, and r. So I should be able to write them down in terms of L, because I have 4 variables and 4 equations. It's going so nice so far. So let us give some name for these equations, equation numbers. So 1, 2, 3, and 4. So you can do whatever type of manipulation you want. I will do one type to get all these quantities in terms of m. So let's first use the equations, the first and the last equation, because I can see I can eliminate p directly. So 1 and 4. If I use these two, I can just eliminate p. So I get m square r to the minus 4 equals m r to the minus 3 into t star. This implies t star is 1m here and m by r star essentially. So that is something new I get. This is 5. Looks much simpler. Now that I know that t star is m by r to the power 4, I can use m by r star. I can use that with the equation 2 and I can write down L. So 5 and 2, let's see what will it give. 5 is m by r, so I get m to the power 4 by r star minus 4, and in the right hand side I have, so these are all tilde equal sign because as you see that they're not equals, and r to the power minus 4. So r to the power minus 4 cancels out from both sides. So you get L star goes as m cube. We already have got, not we have not done much yet, but we have got the mass luminosity relation. So this part where it was supposed to be 4.5, where sun lies, we don't get 4.5 quite well, but we get why it is a power law, and the number is quite close. You can make it even closer if you lift some of the assumptions, but that is difficult. We'll not do that. Okay, let's proceed. So what can I do now? Let us now look at how radius varies with respect to mass. For that, I use the equation 3 now, or sorry, equation 2 now, and I know, no, I use equation 3, and I know how L changes and T changes, so I use that information. So equation 3 and 6 and 5, so I use all three equations. So L star is m cube, m squared, r star to the power minus 3, and t star to the power m, I write from equation 5 as m to the power n by r to the power n. So r star, how is it given in terms of the mass now? So let's work out here a little bit. It looks a little bit more complicated. So this I can write as m to the power, I have 2 plus n in the right hand side. So this is 1 minus n equals r star to the power 3 plus n. So r equals m to the power n minus 1 by n plus 3. So this I will call 7. You see, we start getting everything in terms of the radius. Like now I can, because I know now r in terms, sorry, so we start getting everything. Now you see, we start getting everything in terms of the mass. We got luminosity and radius in terms of mass. We can also write now the temperature in terms of mass if I use 5 and 7. So T star is m by r star. M is just m, and r star is m to the power now minus n minus 1 by n plus 3. So what will that give me? That will give me m to the power So T star I got now how it goes as a function of M. You see, one obviously want to see what happens for the HR diagram. And the HR diagram is a relation between L and temperature. So we can use now 6 and 8 to get the relation between L and temperature. So 6 and 8, if I use together, what will that give me? Okay, so how will I use 6 and 8? That's the question, right? So I start with what I know about the relation of L and T, which is L is 4 pi r square sigma t to the 4, so I'm not writing all the constants, and then t star to the power 4. Now I can write r star square as m to the power n minus 1 by n plus 3, 2 times that, and I still have t star to the power 4. And remember that L is m cube, so m is L to the power 1 by 3. So this is essentially L star to the power 2 by 3 into n minus 1 by n plus 3, then t star to the power 4. One minus 2/3 of n minus 1 by n plus 3 is t star to the power 4. Let's work out what I will get doing all these things. This exponent is 3 into n plus 3 in the denominator, 3n plus 3 into 3, 9, minus 2n minus plus 2. Three n minus 2n is n, 9 plus 2 is 11. Please work this out, because as you have seen, I tend to do a lot of mistakes in calculations. You may see that this number is different, but it doesn't matter because you can always work it out. So L star comes out to be t star to the power 12 into n plus 3 by n plus 11. So if n equals to 4, L star is t star to the power 16, figure out the exponent. So that's your relation for the HR diagram, right? So I can now write that L of a star, luminosity of a star, with respect to the solar luminosity will be given this way. because sun does pp chain, pp cycle, so n equals to 4 for the sun. Or to be more precise, L by L sun, if I take log of it, or let us write this way, log 10 of L is 84 by 15, which is about 5.6 log of t plus constant. This is for pp. Figure out what it is for n equals to 16 CNO cycle. So you see, this is predicting now that if I plot log of L with log of t, there will be a slope of 5.6. That slope, as it was observed, was 5. So even with this very simplified explanations, you explain the HR diagram, at least this part of it, where the main sequence is near to the sun region. The slope was, your prediction is 5.6, the actual is 5. So it's quite close again. Let's ask the question, what will be the age of the star? Age means obviously how long it lives. So lifetime, if you wish, that may be a better word. So the main sequence lifetime, how can I calculate it? It can be that all it's the mass which is giving the energy. And last time we saw that it was epsilon m by L. Epsilon again is a constant, binding energy per unit mass. So this is m by L, L star. L star is goes as m cube. So this is m minus 2. So you see, higher the mass, lower is the lifetime. So you expect that the high mass stars live very less. So high mass stars stay for lesser time in main sequence. That explains why the main sequence is depleted for a globular cluster which has spent quite some time with all the stars. So the high mass stars has gone out of main sequence for a globular cluster. That's why you don't see high mass stars in that. In fact, I can now age the cluster looking at how much high mass star is depleted. That actually is how a cluster is, age of a cluster is found. Unfortunately enough, we'll not be able to do a precise discussion on that. For stars with smaller mass, what happens if the mass of the star is small? Let us see what we have found. Say I am in a pp's chain, n equals to 4. So for mass with smaller stars with smaller mass, n equals to 4. The temperature, that's because the temperature is very small. If I increase the mass, the temperature will increase, right? So which means now for the stars with smaller mass, as I say that pp chain happens, I can say that the temperature goes as m to the power 4 by 4 plus 3. So I can say T by T sun, and this is the how you do the calibration, is m by m sun to the power 4 by 7. Remember that for the PP chain to happen, there was a critical temperature for the PP chain which was to be greater than 4 into 10 to the 6 Kelvin. Okay. So the core temperature of the star has to be more than 10 to the 6 Kelvin. Now what I can do is I can convert this expression. I can say m equals m sun T core temperature of that star by T core temperature of the sun to the power 7 by 4. So this will tell me that if this Tc is less than Tpp, no nuclear fusion, no source of energy, and if the gravitationally bound object does not provide enough source of energy, not a star. So I can calculate now using this expression what is the minimum mass of a star. So the minimum mass of a star will be, in terms of solar mass, is in place of T core I put Tpp, and sun core temperature approximately is known, is about 5 into 10 to the 7 Kelvin to the power 7 by 4. If you calculate, you will see that the minimum mass of a star is 0.08 solar mass. And if I know the minimum mass of the star, you remember that I said that I will calibrate everything in terms of the solar. So I can calibrate in terms of solar luminosity. I can calibrate the luminosity in terms of the solar luminosity. So this, remember that our expression said that it will be like m cube. So the minimum luminosity I can now calculate in terms of the solar luminosity. This is m by m, will I have to put m minimum, which is 0.08 solar mass. So this is at 0.08 whole cube, which is of the order of 10 to the minus 3 solar luminosity. And that explains why you don't see stars which has a luminosity less than 10 to the minus 3 of the solar luminosity. So you see, this very simple dynamical dimensional analysis can explain the minimum luminosity of a star, minimum mass of a star. It explains why we don't see the high mass stars in the globular cluster HR diagram. It explains the slopes of the HR diagram. It explains the slope of the mass luminosity diagram. So this is called the theory of main sequence. And remember, I have not though written all these expressions, equation 4, 5, 6, 7, 8, etc., and so on. They can all be calibrated using the values for the sun. Like this is a calibration of the luminosity scale in the all the stars in the PP chain using the value of the sun, solar luminosity. So for example, if I tell you what is the mass of a star which has a luminosity 2 times the luminosity of the sun, you can just put that in this expression and find out what is the mass of that star, and so forth. So that's it for today. We'll have one more lecture in the stellar structure or stellar physics part of this course, where we will discuss how, using a particular type of equation of state, we have looked at numbers of equation of state, and the equation of state we used here is the ideal gas equation of state, which depends both on temperature and pressure. But we also have cases, which is the degenerate gas case, where the pressure depends only on the density, and it depends differently for relativistic or non-relativistic degenerate gas. So what we'll do is we'll look at such equation of state where pressure depends on a power of the density. So those are called polytropic equation of state. That is what we'll do in the next class. Let me revise what we have done here once again. We said that we will find a theory of main sequence where we will try to explain these observations. And we started with the stellar structure equations with some idealized case assumptions. And we did simple dimensional analysis, which explained eventually at least the nature of these curves. Sometimes the numbers were off, like that 4.5 in the luminosity mass diagram was 3. The 5 in the luminosity temperature HA diagram was 5.4 or 5.6. But that's all right, because we did not even solve these equations, but still explains so much of physics. Before we end our discussion today, let us have a look at the first two stellar structure equations and the case where the pressure is not because of an ideal gas, but mostly because of radiation pressure. So I have these two equations, and we say that the pressure, we are looking at very high mass stars. Now we know that for the high mass stars, the luminosity also is enormous, and then the pressure because of photon or because of radiation will become important. So this has the kinetic gas pressure plus the radiation pressure. Now the radiation pressure, as we have seen, depends on T to the power 4. It does not depend on the density. So I can say that how the radiation pressure changes as a function of temperature is simply I have dt dm as minus 3 kappa by 4 sigma 1 by t cube L by 4 pi r square whole square, and dt I can replace with d pressure. So I get, so dt from this expression I am replacing with d radiation pressure. So p radiation dm becomes minus kappa 4 sigma cancels out, t cube also cancels out, whole square. And this is dp radiation in terms of dm, and this is total pressure in terms of dm. So I can write that d total pressure, dp radiation, let's write this with respect to dp. This I can figure out. I have to just divide this expression from the hydrostatic equilibrium expression. Now let me tell you a little bit about this expression. What this expression is telling, the right hand side is essentially the force of gravity, which is trying to collapse the star. The left hand side is the pressure, and the pressure varies as a function of radius or that mass within that radius. And because of that, the pressure is trying to expand the star. And these two, if they wins, then neither of the expansion or the collapse happens, the star remains as it is. So dpdm, I divide that with dp radiation dm. What you will get is kappa L, and then, okay, remember, this is total pressure. At the surface, both the pressure, okay, not at the surface but towards the surface, or we can say as r increases, which obviously also means that m also increases, both pg and p radiation will decrease. Because remember, at the surface it is supposed to be almost zero if the star has to be stable. If the surface there is a lot of pressure, imagine that the pressure is more towards outside, then what will happen is the star will blow away the outer part. That's what happens in a supernova, but we are talking about a stable star. So if both the pressure is decreasing outwards, p radiation is lesser than the p. So dp radiation, because pressure cannot be, we are not considering negative pressures here, of course, this should be less than 1 at the surface of the star. It's always so also at the surface. So what does it mean? It means kappa, or the L, let me do step by step. Kappa L by 4 pi gmc, which is the right hand side, should be less than 1. At the surface, L is the luminosity of the star. That has to be less than 4 pi g c by kappa. Okay. So this m at the surface is obviously the mass of the star. So now, so because we are talking about at the surface, let me be more precise. This is L star, and this now is the mass of the star. So this divided by kappa times the mass of the star. Okay. So when is this true? When the pressure at the surface is relatively less compared to inside, it's essentially zero to the good approximation, such that the star is not blowing itself apart, the star is unstable. So for HIMA star and high luminosity star, because high mass means high luminosity also, we have already seen that today. There will be an upper limit on the luminosity. If it is anything more, then there will be enormous radiation pressure which will blow the star apart. This is called the Eddington luminosity. Essentially, this gives you the luminosity of not only star, anything, any object which will have cannot have more than the Eddington luminosity. Because if it has more than the Eddington luminosity, the radiation pressure will exceed the gravitational force and that will blow it off. So this comes out to be 3.2 into 10 to the 4 in units of solar and in units of. So the so remember that you have a kappa sitting somewhere. Kappa is in the denominator. So that kappa is considered that of. So this remember kappa comes from alpha, which is the absorption coefficient. So imagine the process which is doing the absorption is the electron scattering. So that is what is sitting over here. So if you assume that, if you assume the mass of the sun to be the mass of the star, then the Eddington luminosity comes out to be 10 to the 4, 3.2 into 10 to the 4 times the solar luminosity. Thank you.